Alright, what's going on, guys? So today we are talking about the coordinate-free notation of the Riemann curvature tensor. In the last video we started to introduce the curvature tensor. We talked about its components, how we calculated it. In this video we're going to go through a lot, right? So this is going to be somewhat of a long video. We're going to cover the Bianchi identities as well, and I'm going to sort of rename them because it helps me remember things a little bit better when it comes to remembering the Bianchi identities. But anyways, let's get straight into the content. Make sure to hit that like and subscribe button. Make sure to hit up my Patreon page too if you're interested in supporting this channel. Okay, we are talking about the coordinate-free notation to the Riemann curvature tensor today. So what we want to do first is we are going to say that this is a tensor. It's a rank 1, 3 tensor. That means if we contract it with a covector, then we should get a number out of this mapping. Okay, so what I did earlier, about 2 videos ago, I've been consistently writing out the Riemann curvature tensor as this right here over the past couple of videos. Now let's expand this guy out and see what happens. So we expand the commutator, or the Lie bracket, into this and this guy over here. We didn't expand this guy because we're going to see actually if we do this for basis vectors, then the commutation is actually just going to go to 0 here because the commutation of 2 basis vectors is 0. So we're left with something that looks like this. Okay. We can now expand this guy, right, to look like this. And so how do I get there? Well, I'm taking the derivative of this and the derivative of this. Okay, and when I take the derivative of this, I get another affine connection. That's where this term comes from. Okay, this is just product rule here to get these two guys. Or these two guys and these two guys. Alright, and then we have our basis vector. And this is our Riemann curvature tensor. Okay. So this whole thing is a vector, right? This whole thing, because a vector has to be contracted with a covector to create a number. All right, so by taking this as a tensor, we were able to recover the coordinate notation for the curvature tensor. Okay. Or for the curvature, right? So I'm being a little bit redundant here for the curvature. So let's recap really quick. Blue period. Before we move on to symmetries of the Riemann curvature tensor. So really quick actually. So the torsion we recall was this. The components to the torsion were this. The curvature of tensor would look like this, and its components much uglier, looks like this. And the basis vectors, again, we have 3 basis vectors here, right? 2 of which are covectors, or vectors, and the other one's a covector. Here, we just have one. This actually is not just one, right? Because this has to be E alpha and E beta. That gives us the components for our tensor, our torsion tensor. Okay. So again, really quick, when we treated this as a tensor, we were able to see that this thing was a vector. We were able to see quite easily compute these guys again just from this definition right here. Okay, so the Riemann tensor has symmetries. What does this mean? In 2D, the Riemann tensor has 16 components. 3D, the Riemann tensor has 256 components. The reason for this is because in 2D, we have this guy can have can run over 2 components. This guy can run over 2. This guy can run over 2, and this guy can run over 2. 2 times 2 times 2 times 2 times 2. Well, that's going to give us 16. And actually this has to be 40, and 40, this is going to be 256, right? Because we're going to get 4 times 4 times 4 times 4. So you can do that if you want. That's going to be 256 components. So, but what we're going to find out is that these 256 components actually, a lot of this will reduce down to very few components because the Riemann tensor has symmetries. These are the 3 symmetries, and I'm going to go about and prove these symmetries now. Okay. And so this one's called the Bianchi Identity. And then these are just symmetries of moving around the indices. All right. So we're now going to prove these identities. We're going to make use of metric compatibility and the torsion freeness. So we want to keep in mind really quick that we got to this conclusion last time by using torsion freeness. We're going to get to these conclusions also by using torsion freeness. So it is assumed from here on out, or not from here on out, but from here until the next few videos, until I say we're not going to assume torsion freeness, it's assumed that everything is going to be torsion free, and we're going to see why this is the case. Okay. If you remember, we had a metric compatible torsion free connection. We talked about that before. Now we're going to have a metric compatible torsion free Riemann curvature tensor. All right. Let's begin. The first symmetry. First symmetry, we take this guy and we say that if we swap the 2 indices, we get this right here. Okay, if we subtract the 2 from each other, actually no, it's not subtract, right? If we multiply this guy by a negative sign, okay, well then we get this guy back, which is this guy. So these u and v correspond to alpha and beta. These are the 2 vectors, the 2 directions that we're inputting into our Riemann curvature tensor. So the directionality, or the direction vector anti-symmetry, is established. This is the first the first Riemann curvature tensor symmetry. So there's symmetry about the last 2 components, anti-symmetry. All right, now we're going to go through the first Bianchi identity, or what I'm going to call the first torsion-free symmetry. Okay, so the Bianchi identity is, what we want to do is we want to compute this guy right here. All right, so this guy is so we're going to have alpha beta. I'm reducing notation so I don't have to write the basis vectors here as well. But just keep in mind that alpha beta, that was a bad alpha, that is equal to that, okay? But anyways, we have, so this guy is right here, this guy is right here, and then this guy is right here. We can now notice if we take torsion freeness, we see beta mu, mu beta, right? So these are just, these things are connections, right? Derivatives of basis vectors. So we have beta mu, mu beta, and there's a minus sign, so those guys will cancel. Alpha beta, alpha beta, beta alpha, alpha mu. So we get these guys, but if these guys are basis vectors, which they are, then these guys are going to go to 0. Because the commutation of basis vectors, again, is 0. So if we assume torsion freeness, then the colored terms are going to cancel, and all the commutators of the basis, the commutator of the basis vectors is 0. And so we get this right here, and this corresponds again to this right here. So the mu, so alpha beta, mu alpha, beta mu. Again, these are the input direction vectors, and then we have mu, beta, and alpha, mu, beta, and alpha. So this is the Bianchi identity, or what I like to call the torsion-free identity. Because the Bianchi identity tells you, the name itself doesn't really tell you anything. If you call it the torsion-free identity, then you can automatically think, oh, okay, if I want to derive this, I need to invoke torsion freeness. So I like to call it the torsion-free identity. Bianchi he was a famous theoretical physicist, and yeah, this identity obviously is named after him. But okay, so now we go about the metric compatible identity, right? So the metric compatible identity was this one. So this one is we swap alpha beta, beta alpha, and mu nu and mu nu over here. So we're really just swapping the first two indices. So let's go ahead and do that one. Metric compatible identity. So what we want to do here is, again, we're just expanding out. We're doing everything in terms of basis vectors. And we're doing this, what we're going to do is we're going to take the Riemann curvature tensor and have it act on an inner product. Okay? We'll see what that does, because we can expand this out. This guy goes to 0 again because these are basis vectors. We can expand this out like this, and we get this guy right here. All right. So E alpha, and then we take the derivative of this. This is just product rule and product rule again. All right. Oop. So let's come up here now. So we have this. And to get from here to here, or this whole phrase right here, is we have alpha beta, or S, and then beta R, and E alpha S, right? So this is, again, we are doing the product rule, right? So applies to this guy because that's a vector, applies to that guy. So that's how we're getting these two terms. This one will give us these two terms. This guy here will give us these two terms. And this guy here will give us these two terms right here. And we notice now I can cancel things out. Right, cancel these guys out. The reason we can cancel them out, E alpha, E beta, S, R. You can see they're the same, right? And we have positives and negatives, so those guys will cancel out, and we get this right here. So those are the leftover terms. All right. So what is this? This is the curvature tensor on the basis vectors acting on R. All right, and this is the curvature tensor on the basis vectors acting on S. So acting on R, acting on S, and then we have this S and this R, this S and this R right here. So if we look at this side of the equation now, we can expand it out again. And since these are basis vectors, we can take derivatives. And since dot products are scalars, this is 0. Okay? All right. So we have that 0 is equal to this, which is up here. And eventually we said that it is equal to this right here, which is right here, just all in terms of basis vectors. Now we're replacing R and S with basis vectors mu and nu. All right. And then we had put some dummy indices in here. We change up mu with I. Or no, we're not changing up mu with I, right? Mu is the vector that's being acted on. Alpha and beta are the two vectors that are the two directions. And then we need so a dummy index to make this a 1-4 or a 1-3 tensor. We do the same thing over here. All right, and then we get to here, right? So EI EV E mu EI. Well, these are just this is just a metric, right? Or this was just the metric. Metric was something that gave us an inner product, or a tool, a tensor that gave us the inner product in our vector space. So we get this. That's going to sum, or this is contraction over an index, and so we get this guy right here. All right, so we can take over one of these guys to the other side, and we find that one is the negative of the other. So this is the metric compatible identity. Right, this is to say that the first two indices, if we swap those two guys, we get a negative. Right, so this is interesting, right? If we just go back really quick, if we swap the last two guys, we get negative, and if we swap the first two guys, we get negative. Right, so now we have one more symmetry we want to look at. This is the second torsion-free identity, because what we're doing here is we're saying, we're going to say this right here. So this right here, this is that Bianchi identity, or the first torsion-free identity. And this is a little bit weird, because we can swap these two guys to get a negative. That's what we said before. Okay. Alpha nu alpha. We can swap these two guys and we get the negative. Right. So the negative of this is positive this. So we get these two guys. And then this guy can expand out into this. This is the Bianchi identity again. And this guy will expand to this one. So I'll just, like that. These are using torsion-free identity again. Right? So this is, or the Bianchi identity again. We find that mu nu alpha beta, this is mu nu alpha beta, mu nu alpha beta. Right, so these guys can actually combine with one another. If we swap these two guys, this becomes a positive. Right, and if we swap a beta alpha, that becomes a positive. So that's why this is 2. These two guys, we can swap as well. Every time we swap something, right, we're changing the sign. Okay, and then we get down to here. And the way we get down to here is we have beta alpha nu mu. So that's going to be beta alpha nu mu. So we're swapping these two guys. So these two guys are going to are going to give us this right here. Right, and so then we get, so once we get from to here, well, we can drop this guy back down here, and we get this. And then we take this guy to the side, and we get this. Alpha, beta, mu, nu. Make it a positive over here, but then swap the index, and when you swap the index, that changes the sign, right? So this is going to get brought over here. It's going to be this plus this guy. So we get this. We can divide both sides by 2. And we get, lastly, the second torsion-free identity. So that one was a little bit, that one's a little bit weird, right? Because it's a lot of just, we reuse the Bianchi identity, and we're looking at swapping indices as we go down this chain of what seemed to be a never-ending playing around with indices, which is kind of annoying. But we get to this point here, which is quite nice. In 2D, So we have all these symmetries, right? So we have all these symmetries, which really reduces down the amount of freedom that we have to play with in this tensor. And so what this means is that in 2D, all these guys are going to be 0, because every time we swap 1 and 1 with each other, it's just going to be the negative of that tensor. So if this, and so that means that these guys are really just going to be 0. So we have these guys equaling 0. We have all these symmetries here. You could pause the video if you want to try to see why this is all the case, right? But we can see, swap these two guys, we get this. It has to be a negative. And then we can swap, we swap, so that's going to be equal to this guy, right? Because that's going to be, alpha beta. So we're swapping these two guys, 2 and 1 and 1 and 1. Okay. And so that's going to equal this guy here. And then we get this. Well, we can also do this guy right here. So we're swapping to get negative again. And this is all 0. This is all 0 as well. So the only options that we have that actually have 1 degree of freedom are these guys right here. So in 2D, the Riemann curvature tensor only has 1 free parameter. This is that 1 free parameter. In 4D, the 256 components gets reduced down to 20 free free parameters. So that's a huge reduction. And I'm not going to do all of that, right? Because that would be a lot of stuff to go. The 256 components. If you really want to see something like that, I might put it on my Patreon page. But you could just take my word for it that this actually gets reduced down quite a bit in 4D. So what looks like a scary tensor actually has a lot of symmetries that we can abuse and use. But anyways, this was the Riemann, a round trip of the Riemann curvature tensor. And I am happy to say now that in the next video, we're going to go above and beyond what a lot of other tensor calculus courses don't go into. We're going to start covering the Weil tensor. We're going to cover other abstract tensors that, and on the way, we're going to talk about more details on geodesics and stuff like that. I'm refraining from invoking a lot of physics into this, because this is a tensor calculus playlist. I'm going to come out with a GR playlist very soon here. They're in the workings. And so, again, if you like this kind of content, make sure to hit that like and subscribe button. Make sure to hit that Patreon page. And I will see you guys in the next one.